So hi everyone, my name is Gurman Singh Buller and today I'm going to talk about a topic product quantization. So let's deep down into the topic that what product quantization is and what the actual concept behind this topic is. So the points that I'm going to cover is what is quantization, what is vector quantization, the concept of product quantization, and the takeaways from this presentation is how quantization actually works and what's the concept of product quantization and why we actually use it. So this is the research paper that I referred for the whole presentation. And let's deep down into quantization. So we can see there are two images. One is on the right, one is on the left. On the right, it's a 32-bit ARGB image. Why is 32-bit? Because each of every frame, that is alpha, red, green, and blue, they are of 8 bits each. So in total, it's of 32-bit. And on the left is just 256 image that is represented by just 256 colors. So what is the space that is required to store all these 256 colors? Is just 8 bits of space. And we can see we have what we actually did. We collected all the points which are of all the colors which are similar in nature and represented all those colors by just a single particular color. So we have made clusters out of it. And by making these clusters, we have reduced the size from 4 times, basically from 32-bit to 8 bits of space. Now talking about vector quantization. So what vector quantization actually is, let's see it with an example. So let's see there are like 10 points, data points over there in a vector. So D1 to D10, there are 10 points. And let's say that, okay, this particular region is representing all the points from D1 to D10. I say that, okay, I don't want to represent each and every point as an individual entity. I want all of these 10 points to be represented by a single centroid value. So I just like find out that, okay, which value is or which value is closest to all the values from D1 to D10 and represented it with a plus sign. So this plus sign is known as a centroid for this particular vector V1, which is represented. And this particular centroid is known as a code word for all these things because it is representing all these particular vectors, and all the vectors which are having this particular code words and the collection of all these code words is known as a code book. And the region which is being represented by these D1 points is known as a Voronoi region. Now, how it actually works. So let's say we have a vector of size 1024, and there are like total 50,000 of those vectors. And we say, okay, we are gonna represent each and every vector by k particular centroids, basically applying k means on it. So what actually now happens, instead of 1024, we have just k values. So the high dimensional vector is of the size 50,000 into 1024, which has been reduced to k into 50,000. So that's how the things changed. Basically, we have reduced the amount of space that is required to represent 50,000 into 1024 points to just k into 50,000, which is much less than the original size. And we have given distinct codes to these centroid values so that in case of decoding, we can decode them easily. Because in this step, we have encoded it, and in this step, we're going to decode everything. So now talking about one more example. So let's see, okay, so this is the whole code book that we have generated. Let's see, there's one new point that is introduced. So let's say x is equal to 0.75, 1.27. This is a new point that we have introduced. We'll find out, okay, this point is nearest to which code word. So we can say this out of all these four, it is nearest to 1 comma 1. So we will match this x with this particular code word in this code book and give this thing a particular index. And this is how encoding works. And when we have to decode or we have to look up the whole thing, we will just find out, okay, this is the index value, and we'll find a particular code word out of it. That's how the things work, the encoding as well as the decoding. Now, coming to one more example. So vector quant, so let's say there are a total of like 0 to 7, there are total 8 numbers. So okay, if I say I want to represent all these 8 numbers separately as an individual quantity, then we need like 3 bits to represent all these 8 points. We have given a representation right over here. And okay, now I say I don't want to represent each and every number individually. I want to represent a set of numbers by a particular value. So let's say I say all the points from 0 to 1.9 will be represented by 1. Similarly, all the points from 4 to 5.9 will be represented by 5. So in this way, I have reduced the representations from 8 to 4. Now I'm just representing 4 numbers, 1, 3, 7, and 5, because these are representing the whole particular set. So how many bits are required to store these 4 numbers is just 4 bits. Now I've reduced the size from 3 bits to 4 bits. It doesn't seem to be a very extensive change, but if we say, okay, we have 1,000 numbers. So in case one, this one, in which we were representing every number by their original or as an individual quantity, we gonna take like 3 into 1000, 3000 bits. And in case 2, we're gonna take like 2 into 1000, gonna 2000 bits. So we have says 1000 bits to save to store 1000 numbers. So if we scale up the things, then the difference is drastic. Let's say, okay, so till now we were discussing about one-dimensional space. Let's talk about the two-dimensional space. So assume that we have 1024 red points. So to represent all these as 1024 red points, we need 10 bits of space. So but now we say, okay, we want to represent, or we going to cluster all these points into different clusters, and there will be a total of 5 different clusters, and each cluster gonna be represented by one particular centroid value. So these are the green points that are representing each and every of these clusters. So now we are just representing 5 different points, which are individually representing a set of particular red points. So now we need only 3 bits of space to represent the data. Now the whole data that was being represented by 10 bits now is just being represented by 3 bits. Such a drastic change. So let's talk about some cardinality thing. So the memory cost of storing centroid is log 2k. The memory cost of whole data set is this formula, but let's now understand with an example in a more layman terms. N is the total number of rows and D is the dimensions. Taking these values that we have taken in the recent example, so the memory cost gonna come out to be 1.09 MB, and the memory cost of the original data set is 204.8 MB. So we have reduced the whole thing from about 186 times the reduction happened. So now, okay, vector quantization seems to be a very nice thing that we can reduce the amount of space that is required to represent the particular set of numbers, but there are some drawbacks as well. So we say, okay, there are total 64 bits of codes. So to represent those 64 bits of codes, we need like 2 to power 64 amount of space as well. So in very large quantities, vector quantization won't work properly because the data is, there's no limit on the data, right? So if the data is tremendously huge, then vector quantization might fail as well. So let's take a step further to understand what the next part is. It's product quantization. Product quantization is the advancement in vector quantization. So what we actually do, we represent all these centroid values. So in vector quantization, we stopped at the centroid values. Okay, these are the centroid values, and we are representing the whole set of numbers by their particular centroid values. But now we're gonna represent the centroid values by a particular one centroid value, which is closest to all the points. So now we are further reducing down the space requirements. Now, this is a very layman explanation. Now coming out to be the example. So the example says, let's set m is equal to 8. M is the number of subspaces that we gonna make, and k is the, like k means clustering k value. So the total amount of data we have is 50k number of rows, and 1024 is the number of dimensions. Now, to store the whole thing is 50k into 1024. Very, very huge amount of space. We have divided the whole thing into 8 different subspaces. So 1024 is divided into 8 different subspaces, coming to be of each of space 128. Okay, now we have reduced down the space to 8 subspaces. Fine. Now we will run k means clustering. So all these 50k into 10 and into 128 points will be represented by just 256 points. So next we can see after applying k means clustering, there are just 256 points that are being that are representing all the 50k into 128 points, and each centroid has having a dimension of 128 because we have divided into 8 different subspaces. Mentioned that. Now we're gonna take one step further. Till now we were doing vector quantization, okay, representing by the centroids. Now we're gonna represent all these points, which all these centroid values, but for each by their closest centroid value, and we're gonna store that in an 8 bits of space. So all these 250s, we're gonna find the closest centroid value to all the points, and we're gonna represent all these points by just one value. So 4096 bits that were required in this condition are now compressed to just 64 bits. So such a huge drastic change in size. So it's 64 bits now. It was 4096 bits earlier. So these are the centroid values. The centroid values are also known as reproduction values, and the set of all the reproduction values, which is also known as a code words, is known as a code book. And a centroid is a concatenation of the centroid values for m So M is the number of subspaces that we have made. So these subspaces, they generate the centroid values, and these centroid values further generate the closest centroid value. Or we, in other ways, we can say we've tried to find out the centroid value which is the closest to all the points, and we represent the whole centroid values by particular one value only. Now, okay, now we have done understood what quantization is and what product quantization is. Now let's talk about how we're gonna do searching with this quantization step. So there are two types of methods. One is exhaustive searching method and one is the non-exhaustive searching method. So in the exhaustive searching method, what actually happens is we're gonna look upon all the data points. Whereas in the non-exhaustive search method, by some pre-processing steps, we're gonna say, okay, we're going to look into this particular section of the data set and we're trying to find out the results in particular section, not looking all the data points. So let's talk about exhaustive search methods. There are total two types of methods. One is the symmetric distance computation and other one is the asymmetric distance computation. So in the asymmetric distance computation, uh, we take the centroid values of the query point as well as the centroid value of the data point as well. So the distance is approximated by the distance of query vector as well as the centroid value of the data vector. So we're taking it an example. So there are two x and y points. Y is being represented by its centroid value q of y, and x is being represented by its centroid value q of x. And we are finding the distance between these centroid values, not the actual values. That's the symmetric distance calculation is. So one particular question, like, is it need to calculate the square roots? The answer is no, because square root is a monotonic function. So the ranking would be same for sure. Now, asymmetric distance computation. In asymmetric distance computation, we take the centered value of the data point, but we don't take the centered value of the query point. So query point is the actual query point. So x is the query point. So we have taken the actual x value, that is the basically coordinates of the actual point, but we have taken the centroid value of the data point. So we are calculating the distance between the actual query point and the centroid of the data point. Now, okay, we have discussed these two things. Let's talk about the comparison of these two things. So the preparation cost, the query preparation cost is almost the same for SDC and ADC. But SDC, it limits the memory usage because we are taking the query points or the centroid values for both query point as well as the data point. And ADC, but got an edge over SDC because we are using or we are just taking in account the actual coordinates of the query point. So the accuracy is increased in ADC as compared to SDC. So wherever we are having a trade-off, okay, or we are not concerned about the memory consumption, we can anyhow prefer ADC over SDC because ADC gonna give us more accurate results. So thank you so much for everyone for listening. That's my presentation on product quantization. Thank you.